Okay, so this is going to be a refresher lesson on how to do acid-base stoichiometry. Weirdly enough, not sure everybody remembers how to do this. So, in an acid-base reaction, there's three basic types of reactions you guys need to worry about. Once it produces solids, so that's precipitation. Once it produces liquids like water, which is acid-base. And once it basically produces a gas, so that could be combustion, decomposition, or trading electrons, things like that. But basically, acid-base is a big category of its own. It's a double replacement reaction where water forms instead of a solid. When they react in a neutralization reaction, it doesn't matter if they're strong or weak. Okay, so we've talked a little bit about what weak acids are like and strong acids are like. But when it comes to neutralization, they behave the same way. And the reason why they behave the same way is stoichiometry happens first. And all the stoichiometry happens in terms of moles based on the moles ratio. When the moles of the acid equal the moles of base, according to the balanced equation, it's at what's called the equivalence point. That's the definition. When the moles of the acid equal the moles of the base, according to the balanced equation. And for a solution, this is the way you find the moles. So now, the reason it's called neutralization is because an acid neutralizes the base or the base neutralizes the acid. They generally take place in solution. So you'll be using molarity to determine moles. And you are only interested in the moles of the acid and the base. We don't worry about products at all. No one cares how much water you make out of this. And you're going to use the process of titration to determine unknown concentrations or unknown moles. And that's what we're going to do in the lab this week. At the endpoint, it's called endpoint because you stop the titration. There is something called an indicator in there. It will change color. The indicator changes color at the endpoint. The endpoint should be close to the equivalence point, but there's no other way to know what the equivalence point is without having that indicator present to change color. The way you do a titration is you take a solution when you know the molarity, and you add it to an unknown until the equivalence point is reached where enough titrant has been added to neutralize it. Technically, this should say moles, but it's the same idea. Okay, this equation we've seen before. It will work only if both your acid and your base are dissolved in water. The way it works is it's molarity times the volume over the acid coefficient, molarity of the base, volume of the base over the base coefficient. Volume can be milliliters or liters. More likely it's going to be milliliters. But it'll work only if everything's aqueous. If you have a solid in there, it doesn't count. So for this one, what volume of AlOH3 can be neutralized by HCl? So HCl plus AlOH3 always needs the balanced equation, H2O and AlCl3. Double replacement reaction. Balancing it, I have 3 OHs, I need 3 HCl's. So I'm going to do MaVa over the acid coefficient equals MbVb over the base. And it doesn't even matter which one you know is which, as long as you know the 3 goes with all the numbers for HCl. So 0.3 times 100 over 3 equals 0.1 times x over 1. Now you might notice this cancels out. That means x is 100 milliliters. These are, generally speaking, if the numbers are nice, relatively easy to do without a calculator. Okay, one of the things you're going to be doing in the lab is you're going to use something called potassium hydrogen phthalate. Okay, potassium hydrogen phthalate is used to standardize a solution of NaOH. The problem is NaOH, when you put it in a container, has a tendency to react with the container, so its molarity changes slightly. So right before you do a titration, you need to know what the actual molarity is. And they use something called KHP because they can purify that really, really well. And it says it takes 75.2 milliliters of the NaOH to react with the KHP. Now, the balanced equation is 1 to 1. Okay, and they tell you the molar mass of the KHP. So at the equivalence point, or neutralization point, the moles of NaOH equal the moles of KHP because it's 1 to 1. So I'm going to start with 1.352 grams 204.22 grams, 1 mole. Takes 1 kHp to react with 1 NaOH. Notice I am not doing the MAVA thing. And the reason I'm not doing that is because it's a solid. You can't do it if it's a solid. You can only do stoichiometry. So what I end up with is 0.00662 moles of NaOH. So that's how much NaOH I must have had to neutralize that kHp. So the molarity of the NaOH is going to be the moles over the liters of the NaOH that it took to make that happen. Nope. And I get 0.0880 molarity. Now, this has 4 sigs, that's 4 sig figs, that has 5 sig figs. Technically, I suppose this should be a 0 here and a 0 here, but I should only have 3 sig figs at the end. Titrations are a big thing for sig figs. They can be really, really accurate. Okay, so 3 sig figs for my answer. Okay, next one. Now we're talking a solution again. I see milliliters and milliliters. So all we need is a balanced equation, HCl, BaOH2. And again, there's 2 OHs, so it takes 2 HCl's. So I'm going to use the MAVA equation, 0.25 times 300 over 2, because that's all about the acid, equals x times 150 over 1. This crosses out to 150. X is 0.25 molarity. Okay, last question. You're also going to do this in a lab. You're going to take some unknown solid acid, HX, only 1 proton. You're going to react it with NaOH, automatically 1-to-1. If it says grams, that means you cannot do the MAVA thing. So we have to figure out how many moles of NaOH we have. Liters times molarity gives you moles. So 0.0652 liters, 1 liter, 0.825 molarity, and it takes 1 NaOH to react with 1 acid. Stop it. Means I have 0.05379 moles of my acid. Since they are titrated, that means they've gone to the endpoint or the equivalence point. The moles of the acid equal the moles of the base at the equivalence point. So if I take liters times molarity, I get the moles of NaOH, and I know the balanced ratio is 1-to-1. That tells me my moles of my unknown. Molar mass is grams divided by moles. And I get 136.6 grams per mole for my unknown. Okay? So you can use stoichiometry all the time. As long as you remember liters times molarity gives you moles, it'll work every time. If you want to use that shortcut MAVA thing, totally okay. But remember, it doesn't work if it involves the word solid.